Yeah, so I'm Yoonho Park, and most people call me Yoon. People seem to have trouble with 2 syllables. I don't know why. So I've heard pretty much every permutation of my name possible. So I manage a couple of teams at IBM Research. One of the teams I manage is actively developing software for the Coral systems. Now, we're not responsible, of course, being research for delivery of the Coral systems, but we help IBM systems a lot. Now, another part of my team, or another team that I manage, they're putting a lot of thought into how do we take the technologies that we're developing for these high-performance computing systems and apply them to cloud infrastructure, to cloud middleware, to emerging workloads in the cognitive area. So, for example, machine learning and deep learning. Can we actually do really large-scale machine learning and really large-scale deep learning applications? So, my talk is actually 2 parts. I'm going to talk about our design philosophy for these systems, for our high-performance computing systems, and that's a data-centric approach. And then I'll talk about how we're leveraging OpenPOWER, but also how we are feeding back our experiences and knowledge to OpenPOWER. So have a bit of a feedback loop there. So I don't think that we need to belabor any of the points on this slide. We know that we're hitting a lot of hardware roadblocks, and so we need to rethink how we're building our systems. And same with this slide. Many of the speakers here have made the point that we're seeing a convergence of analytics and HPC workloads. I think it was a gentleman from HPE, Eng Lim. He had a really good slide. I took a picture of it because I wanted to perhaps plagiarize it in the future. On the HPC side, he made the point that, well, you start off with small number of inputs, and then you generate a lot of stuff. But then on the other side, on the analytics side, you typically have a large number of inputs, and you then have a small number of outputs, like a thumbs up or a thumbs down type of thing. And that's been our experience as well. Okay, so the approach that we decided to take several years ago when we started thinking about the Coral architecture is what we call data-centric systems. And we want to move compute to data. Now, well, of course, that's an obvious statement, but, and actually many people here have done that. But what we're trying to do is we're trying to do that throughout the whole stack, all the way from applications. So I think it was Stephen from Intelligent Lights talking about in situ computation. Yes, that's very good. But then we also had, I think it was Jerry from Mellanox. He was talking about doing computation in the network. So that's great as well. And we're trying to push that all throughout our hardware and all throughout our software. Okay, and I'll try to show examples of that in our Coral systems and how we're trying to push that into OpenPOWER as well. Okay. Now this is our version of Eng Lim's slide. Okay, as you probably know, we have many different ways to characterize applications. The days of LinPack in the corner, way down here, are hopefully over. Although I guess we'll have the top 500 for quite a while. But what we're seeing is a lot of different types of workflows. I don't know how many of you have had a chance to go through the ECP workflows, but it will make your head spin once you start going through those workflows. But it's a different kind of challenge than we've had before, which is great. Right? Okay. This is another way of that we explain this to people. But this also brings out something else. So here we have the analytics side, and here we have the traditional HPC side. But I threw this graph in here, I threw this slide in here because something else we're seeing is that we really need to have a very modular system because different customers have very different computing needs. And it's not only in size, but also flexibility in how you deploy. And that, of course, leads us to thinking about cloud infrastructures and things like that. So what exactly do we mean about data-centric systems versus compute-centric? Up here we have a traditional computing system. You take the data from the storage, works its way through main memory, through the caches, and then eventually to the processor. What we're trying to push very hard with data-centric computing systems is we want to do computation everywhere. And I apologize to Jerry before my talk because I realized when he was giving his talk that I forgot to put a storage component here where you can actually do computation as well. So I'll apologize again. Sorry, Jerry. I'll add it after I get back to my office. But you know, he's proposing with, well, not proposing, they've actually implemented with Sharp that you actually do computation for reductions in the network, which is great. Okay? And you know, we're exploring you know, how to push computation out to main memory, how to push it out to storage class memory, and storage itself is too. Okay. So what are our exact design principles that we've been working through? Of course, the first principle is minimize data motion because data motion is expensive. Things like the intelligent light in situ experience, we're definitely trying to learn from that. We want to enable compute in all levels of the hierarchy. You know, a GPU, when you take a step back, you're really bringing computation very close to memory. And we have other projects in-house where we're trying to even push it even closer to memory as well. Another principle is modularity, and we believe this because we have seen very different computing requirements from our customers. And principle 4 is basically co-design. And we found that co-design is absolutely necessary, as many of you have stated already during the forum. With the Coral project, we have co-design pretty much throughout the project. At the application level, we have what we call centers of excellence, and we're helping the application teams at Livermore and Oak Ridge port their codes on early access systems. At the software level, we have regular working group meetings in which we give them updates on the functionality that we're implementing. So that they're not going to get any surprises when we give them code drops. So you know, they're really partners along the way, both Livermore and Oak Ridge. When we first started the project, it did seem kind of odd to bring them so close into the implementation process, but we think it's worked out great. It's smoothed over a lot of potential misunderstandings. And they've helped us improve what we're going to deliver to them, which is great as well. Okay. The final principle is that we want to leverage OpenPOWER. Now, of course, in the past, we've been a very you know, strong hardware company, and we still are a very strong hardware company. And you know, we want to use that history to continue to bring value to our customers. Okay, so this is the IBM OpenPOWER HPC roadmap. Let's see. Well, I probably need to update this slide. This is last year. Last year we had Power 8s with the Kepler NVIDIA GPUs and FDR InfiniBand. This year, these are our Minskys, which have Pascal GPUs. They also have NVLink 1, the first generation of NVLink, and EDR InfiniBand. These are, of course, GA'd. You can purchase them anywhere. And these form the basis of the early access systems at Livermore and Oak Ridge. These are the systems that they're beginning to port code to now. Okay, so sometime this year, the hardware verification is going quite well. We will release what we're calling the Power 9 processor, along with Volta. The enhanced NVLink is something that we're very excited about, NVLink 2.0. It gives you a lot more bandwidth than NVLink, approximately 2x, but it also gives you hardware coherency between the CPU and the GPU. Now, something that I kind of glossed over before is the Capi Interface. And this was our attempt to tie together accelerators and CPUs more tightly. The hardware coherence that you're getting with NVLink 2, that's another way that we're tying CPUs and accelerators sort of close together. The accelerator in this case, of course, is the GPU. And of course, we are enhancing Capi as well for other types of devices that we're connecting to our Power 9 processor. Okay. Of course, this is more of a marketing slide about OpenPOWER. What we're trying to do with OpenPOWER is to develop a very rich ecosystem around our OpenPOWER architecture. Actually, if you have much more specific questions about OpenPOWER, we actually have somebody from IBM who was working with OpenPOWER, Brooke, back here. So I found that kind of interesting that they asked me to give the OpenPOWER talk as opposed to Brooke. But if you do have questions, he is hanging around. I think OpenPOWER allows us to do is to really collect a lot of information from customers and get that feedback to our architects. A lot of them are based in Austin, and to iterate and to really improve our system. We are definitely contributing a lot to the software ecosystem. And before anybody asks, no, we're not part of OpenHPC, but we still contribute quite a bit to open source, and we're a very strong believer in open source. Okay? And these are just some of the members that we have. Brooke, do you know what the number is now? Okay, over 300, yeah. So I don't think this is anywhere near 300 right here. But we see a lot of potential in working with all these customers. We are really pushing hard on things like OpenCapi to make sure that they can work well in the OpenPOWER ecosystem. Sorry, OpenCapi is the next version of Capi that we will be releasing. We're trying to make it easier by making changes to OpenCapi. We had some complaints that, the translation work that you're pushing on us, it's a little hairy. Okay, well, what we did was we took that and actually added it to the power processor so that there's less work that has to be done on the device side. So that was feedback that we took and directly applied to our OpenPOWER ecosystem. Okay, as I stated before, the Coral systems are our first instantiation of our data-centric system approach, and the first really big installations of OpenPOWER based systems. We have one that will, of course, be installed at Oak Ridge, and one that will be installed in Lawrence Livermore. Another place where we're doing a lot of work is STFC, Science and Technology Facilities Council. The difference between these two is that the Coral systems are definitely more focused on HPC, while the STFC work is much more focused on analytics and cognitive workloads. They have much more, let's see, how should I say, industry partnerships. So for example, they're working quite closely with Rolls-Royce, companies like Unilever, and that's where their emphasis has to be. They want to really go out and help the industries in the UK. Okay, just some details about Sierra and Summit. This may be old news to many of you. But what we want is to have at least 5 times what we have right now with Titan and Sequoia. It's approximately 3,500 nodes, and they're Power 9 CPUs with multiple GPUs. Livermore wanted a different number of GPUs than Oak Ridge. We will have NVLink 2.0. We have a very large amount of memory on each of the nodes. And as I stated before, it's all hardware coherent. We have 40 teraflops peak performance per node. And we will definitely have EDR by the time we deploy. And of course, we have kept our file system business, so GPFS will be deployed. I guess it's called Spectrum Scale right now. And we will have a disk capacity of about 120 petabytes. So I just wanted to say a few words about the programming approach that we're taking, because this is really where we're trying to push the data-centric system principles with respect to CPUs and GPUs. In the past, in the accelerator approach, you had what we call sort of a copy-only model. You didn't need to have memory to be coherent between the CPU and GPU, but you had to physically, or you had to direct the copies. Now, NVIDIA is trying really hard to make that a lot easier with something called unified memory. But through unified memory, you had to provide coherency somehow, because the programmer doesn't want to have to think about it. And so what they do is that they still copy pages back and forth between the CPU and GPU. Okay? Now, so for some applications, that's fine. But what we really want to have is computing in a shared address space. Okay? And to really get there, we felt we really needed to have this CPU-GPU hardware coherency. And now, for the P9 Volta system, it's not full hardware coherency, but we do share cache lines, okay? And from the GPU to the CPU, not vice versa. So to the actual application writer, it appears as being fully coherent, okay? Now, the challenge, though, is that we still have to manage the NUMA characteristics, okay? And that's something that we're actively researching, at the moment, and we're making changes to the Linux kernel to support this. Okay. So just to drive the point home, here I have a very simple picture of a GPU with its memory, another GPU with its memory, and then the CPU with its memory. What we really want to be able to do is we want to be able to have all of these things just to be peers of each other. So this is the traditional view. Here we have an MPI task that's crossing the CPU and a GPU. And the data and the compute flow is pretty much what you see here. Okay, you compute on the GPU, the data goes over with it, then it comes back to the CPU. Okay. What we're really targeting is what we call peer processing. Data lives where it's needed, okay, and this is what we are going to get with the hardware coherent memory, and the compute flows between the CPU and the GPU as needed. Okay. Now, of course, as I said, this is still under development, but we are rolling it into OpenMP, OpenACC, and CUDA as well. And this is what we hope to deliver for the Coral application writers. Okay, so that's one example of how we're trying to improve the programming models for an existing system. What does the future bring in terms of being able to program data-centric systems? We don't really know, and that's why we created this very obfuscated slide here. On the one side, we have support for big data workflows. On the other side, we have support for HPC workflows. I'm sure that you've seen many of these these systems in the middle here. And while we don't know what we will end up with, we're very confident that we're going to have some sort of convergence in the middle, which we'll call our exascale runtime and middleware. And so we're investing on both sides. You know, I mentioned the teams that I manage. We do have people contributing to MPI and OpenMP, to PAMI, of course, UCX, verbs. But then on the other side, you know, we're working hard on things like Spark. I was happy to hear that Ron at the San Diego Supercomputing Center is also working on something called GATK, which is from the Broad Institute, a genomics toolkit. We're putting GATK in Spark and trying to scale it. Okay? And we're taking HPC technologies to help the scaling. For example, RDMA. So the shuffle that we have with our Spark, it's RDMA supported. It's supported by RDMA as opposed to TCP sockets, and that helps significantly improve the Spark shuffle step. Okay. So just a few words about how we're actually feeding back to the OpenPOWER effort. I already mentioned that we are adding NUMA support to Linux for hardware coherent GPU memory. Linux already has a great deal of NUMA support, but it assumes that you have a schedulable compute element with each of the NUMA nodes. Of course, GPUs are not scheduled by Linux right now, so we're adding support to have NUMA nodes that with just GPU memory, which the Linux kernel doesn't schedule threads on. For provisioning, we are contributing a lot to XCAT because that is going to be our provisioning system. On the burst buffer side, we're adding support for fast shared file checkpointing. Many people do multiple file checkpointing, but many people also use one large shared file for their checkpoint, and that's support that we're adding. We are doing quite a bit of work in yet another cluster system management system. We are adding quite a bit of diagnostics and quite a bit of analysis there. Compilers, our OpenMP work is going into LLVM. And tools. Now, this is one area where we're not making direct contributions to tools, but our approach has been make sure that we at least give the APIs to the tools developers so that they have what they need to help application writers. Okay, so in summary, since I have 5 seconds left, our experience and our observation is that we have this convergence, and the approach that we are taking to address this convergence is this data-centric systems approach. And of course, we want to do this in an open ecosystem. We're not quite sure about OpenHPC yet, but we do want to foster this OpenPOWER ecosystem as our open ecosystem. Okay. Thank you. Tom?
Quick question on the unified memory. I know we were talking about this earlier. Thing for you, Sammy. Okay. So quick questions about unified memory. So one of the mechanisms we're using to do a lot of the memory management specific to our CUDA models is using thrust to do thrust is a very nice way to use a device vector semantics to move data to the device. And right now, as far as I'm aware, and I could be wrong on this, thrust doesn't have any specific support for utilizing unified memory under the hood. It's still using, I believe just standard CUDA malloc.
Standard CUDA, okay.
I believe so. I'm not 100% sure of that. Mm-hmm. So the questions, I have 2 questions. One, is there going to be, do you know of any efforts that's going to potentially be unifying the use of thrust to utilize unified memory? And 2, in an even broader sense, one of the tricks of using unified memory in general is that even if you use unified memory, if I have, say, a standard CPU, let's say a C++ object-oriented code model, right? And I'm still using, say, standard library
Yeah, STL.
mechanisms to do all my memory management. You know, so all my data ultimately is sitting in vectors in various places or something.
Right.
Is there any efforts underway, for example, to allow the vectors to actually allocate to unified memory, so that those then would be actually immediately available? Because that's ultimately what the issue is, right?
Sure.
Even if you use unified memory, you would still basically have to take your object classes that you've originally written for some application on the CPU, and in order, even using unified memory, you would still have to do that extra call to put that memory into unified memory to be accessible by both.
Yeah. So actually, what we are targeting is a unified memory in which malloc memory, as opposed to CUDA malloc managed memory, can be migrated back and forth between CPU and GPU. Yeah, yeah, exactly, and that's because we got a lot of feedback from the labs. This is actually more from the Livermore side. They had applications that were using 15 libraries or more, and when we told them, oh well, you might have to convert all the memory allocators and those to CUDA malloc managed, they said no way. Okay, so that's when we started putting a lot of thought into, okay, how can we support migratable memory for malloc memory, so they wouldn't have to change those libraries, and that's what we're trying to bring online.
That would be a model that would be very useful.
Okay, yeah. So I'm pretty sure you know the hypergroup, at Livermore. They're the ones that are really pushing the bleeding edge with these kind of things. Oh yeah, definitely, yeah.
That would be very
definitely.
Ultimately, it's the issue of several 100,000 lines of these application codes already in existence. And whether it's you're using unified memory or shared or global memory or what have you, there's still a mechanism you have to go through to get the memory there.
Yeah.
It needs to change.
Yeah, exactly. So that's where we're headed with the peer processing model. Yeah, we want to get rid of that.
Yoonho, how are you seeing any in places like in Europe and China? Are you seeing any resistance to HPC technologies from a U.S.-based vendor?
Okay, so I don't know about Europe. I'm not as tightly coupled over there, but we have been helping quite a few proofs of concept. The systems team with quite a few Chinese companies that want HPC systems. And they're able to get pretty good prices, pretty good value from companies like Supermicro or Red that are taking the OpenPOWER designs and creating boxes. So I don't know about Europe, but China really seems to be doing well.
Thank you. Quick question. Just
sure.
Based on your couple of comments around OpenHPC, are there many fundamental barriers for you guys to join OpenHPC, or what do you see as an issue?
Darn, I thought I'd mentioned OpenHPC enough. So full disclosure, Bob and I play a lot of tennis, and so this has actually been discussed before. We're taking a wait and see approach with OpenHPC. I mean, we certainly understand Intel's motivation for this because their install base is much larger than our install base. Okay, so that makes a lot of sense, and so that's why we were very encouraged when ARM is going, head first into OpenHPC. We're a methodical company, right? We put a lot of thoughts into our steps, so that's what I think we're doing with OpenHPC.
Okay, thank you very much.